Okay, let's talk about pressure volume loops. Why do we care about pressure volume loops? Because the truth is that they're not used on the wards that often. No one pulls out a piece of paper and draws a pressure volume loop for a patient on the wards. But they are important for the first step of the boards. And why is that? Well, for one, a pressure volume loop is a visual representation of the entire left ventricle's cardiac cycle. Everything you need to know about volume and pressure, it's all right there. The other reason is that people use pressure volume loops, at least in preclinical years of medical school, to explain the hemodynamic effects of heart failure and valve disease. And because of that, you're tested on it. These are classic board questions. So I would take pressure volume loops seriously, at least through our course and step one of the boards. This is what first aid for the boards has for pressure volume loops. It is a mess. Our goal is to walk you through in a systematic process to have the foundations of what a pressure volume loop is. And to be able to do these things, we want you to be able to draw one and label the axes related to the events of a cardiac cycle. We want you to be able to identify stroke volume and stroke work. We want you to define ejection fraction and calculate it just from the images on the pressure volume loop. Then we want you to describe how the pressure volume loop can be changed by changes in preload, afterload, contractility, and compliance. You've heard those before, and they all usually go together. A change in preload affects change in afterload, change in contractility, but we're going to talk about it only in isolation, because otherwise it just becomes really, really difficult. And finally, we're going to take everything you learned and draw a pressure volume loop with changes that happen in exercise. Okay, let's start with just drawing it. Here is on the x-axis, you have volume, and on the y-axis, you have pressure. You may remember that most of the time you've seen volume on the y-axis and pressure on the x-axis, which is compliance. This is the complete opposite. It's pressure on the y-axis and volume on the x-axis, which is the inverse of compliance. That inverse of compliance is called elastance. Same numbers, just upside down. Now I want you to go and look at an EKG. When you have an EKG, as soon as you hit that contraction, you can see that the left ventricular pressure goes up. And then as the heart starts relaxing, and it goes down. This is part of the Wigger's diagram right here, where you lay on top the EKG and the left ventricular pressure. Boom, contraction, pressure goes up, you're in systole, and then the pressure starts to go down again. What happens in the left ventricle's volume? Well, again, as you contract, the pressure goes up, and then all of a sudden the aortic valve opens, the left ventricular volume goes down to a point until the aortic valve closes, and then the volume starts to go up again. So now let's put it all together, and you can see this in a pressure volume loop. It is just a thing of beauty, isn't it? We are essentially taking the left ventricular pressure graph during a single heartbeat and the left ventricular volume graph through a single heartbeat and laying them together on this pressure volume loop. Okay, let's talk about isovolumetric contraction, systolic ejection, isovolumetric relaxation, and diastolic filling. And let's label them on the PV loop. Let's first start with A, the isovolumetric contraction. Contraction occurs right at the QRS, and you have, right here on the pressure volume loop, an increase in pressure with no change in volume. And then let's go to systolic ejection. You see that there is a decrease in volume and initially a slight uptick in pressure, that's the systolic pressure, and then it starts to go down again. And then what happens after systolic ejection? You have relaxation of the left ventricle with no change in volume. This is called isovolumetric relaxation. And then what happens? Well, then you have diastolic filling. This is where you have a large change in volume for a fairly small change in pressure. And at this point, you've completed the entire cardiac cycle of the left ventricle. And now let's do the same thing with the valves, the mitral valve and the aortic valve. We can again have a PV loop and look at the Wigger's diagram, and then we can demonstrate right where you have the mitral valve open. That happens right at the beginning of isovolumetric contraction. At the end of isovolumetric contraction, you have systolic ejection, which is when the aortic valve opens. Systole ends when the aortic valve closes right at the beginning of isovolumetric relaxation. And at the end of isovolumetric relaxation, you have the mitral valve open, which is the beginning of the diastolic filling. And again, you've completed the whole left ventricle cardiac cycle. Let's go on to the next learning objective, which is identifying stroke volume and stroke work from a pressure volume loop. In order to identify stroke volume and stroke work, we need to know where different volumes are in the pressure volume loop and where different pressures are on the volume loop. Let's start with these pressures and then volumes. The aortic systolic blood pressure is right here at the very top of the pressure volume loop, the highest pressure. The aortic diastolic blood pressure is right where the aorta opens at the beginning of systole. The ventricular end diastolic blood pressure is right before isovolumetric contraction. This is where the mitral valve closes and filling ends. End diastolic volume is here at 120, and end systolic volume is right here at 50. We'll go through these once again as we calculate stroke volume and stroke work. Here's a pressure volume loop. And we need to remember two formulas in order to understand stroke work. One is stroke volume and the other is mean arterial pressure. Stroke volume is equal to the difference between the end diastolic volume and the end systolic volume, both of which are labeled on a pressure volume loop. End diastolic volume is right here. It's at 120 milliliters. And end systolic volume is right here. It's at 50 milliliters. So the stroke volume is 120 minus 50. And you come up with 70 milliliters of stroke volume. Now what about the mean arterial pressure? Remember, mean arterial pressure is equal to 1/3 the systolic blood pressure plus 2/3 the diastolic blood pressure. And where do you find systolic blood pressure on a pressure volume loop? You find it right here, at the very highest pressure in a pressure volume loop. That makes sense. And you can see if I take it over to the y-axis, I get about 120. How about the diastolic blood pressure? The diastolic blood pressure is right where the aortic valve opens. That's the definition of the diastolic blood pressure. And again, I can take it all the way over to the y-axis, and you can imagine it's about 90 here. So the mean arterial pressure is 1/3 120 plus 2/3 90. And you get 100 millimeters of mercury. Now, we've talked about stroke volume, but what about stroke work? Now let's talk about stroke work. Stroke work falls back on physics yet again. Work is equal to force times distance. Volume work is equal to volume times pressure. Now let's equate that to the left ventricle. Stroke work is equal to stroke volume times the mean arterial pressure. In this case, we have a stroke work of equal to 70 milliliters times 100 millimeters of mercury. Is anyone going to ever ask you to actually calculate stroke work? I don't know. I probably won't. But what I would want you to know is that stroke work is the amount of this entire pressure volume loop. And you could imagine as the pressure volume loop gets bigger, you have more stroke work. And as it gets smaller, you have less stroke work. That's really what I want you to know. Okay, let's go to the next learning objective about ejection fraction and using the pressure volume loop to calculate it. Again, here's a pressure volume loop. Ejection fraction is equal to the stroke volume divided by end diastolic volume. That's just a definition or an equation you need to know. Again, here is the end systolic volume and here is the end diastolic volume. Stroke volume is equal to 70. We already calculated that earlier. And we can just divide 70 by 120. And we get an ejection fraction of about 58%. It's that simple, as long as you can remember that ejection fraction is equal to stroke volume divided by end diastolic volume. Okay, I recognize that those learning objectives were quite difficult, but now this is the actual really, really hard learning objective. It is describing how the pressure volume loop changes with changes in preload, afterload, contractility, and compliance. And I will emphasize in isolation. Why do I emphasize in isolation? Because some things are not actually true, but you sure wish they were. just like you wish the Easter Bunny were true, and you wished that Kanye and Kim will actually stay together. It's not going to happen, but you can live for a moment. The deal is that afterload and preload and contractility are all this mess, and they change everything. But we're going to understand these things in isolation. Okay, changes in preload. Here's a nice pressure volume loop. This is where preload is, and you know this because preload is the stretch of the left ventricle at the end of diastole. Preload is proportional to the end diastolic volume, which is just that right there as well. Now I want to show you this graph one more time. There is a relationship between pressure and volume that looks like this. That is called the end diastolic pressure-volume relationship, and it shows you the change in pressure over the change of volume for the left ventricle when the left ventricle is relaxed. In preload is just right here where you end it, and you can imagine that if you have more preload, it'll be right here, and if you have less preload, it'll be right here. Here's an example as well. This is the end diastolic pressure-volume relationship. Here is one preload, now a little bigger preload, a little even bigger preload. So if you learn that a patient has an increase in preload because maybe they gave them volume or blood, you will move the end diastolic volume along this curve. Here's another way to look at it. Let's look at the graph on the left. This is control, this is change. You can see that this patient has an increase in preload from about 120 to 150. And now look at the graph on the right. If this is the control and this is change, you can see that the patient had a decrease in preload from about 120 to 100. Okay, let's move on to changes in contractility. Again, in isolation. We've got a nice pressure volume loop, and we've got this pressure volume graph. I'm going to draw you a line right now. This line is incredibly important. It represents contractility. How do we come up with this line? Well, it is the end systolic pressure volume relationship, and it comes from change in pressure over change in volume. Again, the elastance of the ventricle. However, whereas the curve I just showed you for preload is the elastance of the left ventricle during diastole, this is the elastance of the left ventricle during systole. It's the change in pressure over the change in volume when the left ventricle is completely contracted. I dig that stuff. Not important for you, but what is important is that you recognize that this line is contractility. I can also draw it on a pressure volume loop. It's tangential, that's a fancy word, to the end systolic volume, and it hits this x-intercept right at some magical point where there is no pressure in the heart anymore, but the heart is still contracted with a certain volume. Why is this important? Well, contractility changes in the heart sometimes. When you exercise, you have an increase in contractility. If you suddenly have heart failure, you have a decrease in contractility. And that's what will change the slope of this line. Increased contractility looks like this. It's a steeper slope. Decreased contractility looks like this, a less steep slope. Here's a couple examples of pressure volume loops that change with differences in contractility. Here we have the control pressure volume loop in gray. We have a green pressure volume loop that has less contractility associated with it. And you can see, if you can see this line right here, which is the end systolic pressure volume relationship of the control, this one has a less steep line representing less contractility. And alternatively, the pink has a much steeper end systolic pressure volume relationship representing a heart with increased contractility. Let's move on to changes in an afterload. Okay, here's a nice pressure volume loop. Remember, afterload is proportional to the pressure the left ventricle ejects against. It's proportional to diastolic blood pressure. But really, afterload is the entire ventricular wall stress that it feels during systole. So, the diastolic blood pressure is definitely proportional to afterload. And if you want to end right here and not listen to the next 10 seconds, you can. Most of the time, if the diastolic blood pressure goes up, the afterload goes up. And in fact, Boards and Beyond says that afterload is just diastolic blood pressure. But the truth is that afterload is actually the entire part of systole, and afterload is proportional to not only the diastolic blood pressure, but also the systolic blood pressure, and also, most importantly, the end systolic blood pressure. Afterload affects all of systolic ejection. So how do we do changes of afterload on pressure volume loops? Remember, 95% of the time, a change in afterload is simply just an increase in the diastolic blood pressure, which is right here. But afterload also, this point is also very important, the end systolic volume, the end systolic pressure. Let's talk about why. Okay, let me draw you a line here. This line, again, is the change in pressure over the change in volume of guess what? If we've talked about the change in pressure and the change in volume of the left ventricle during diastole, originally with preload, we talked about the change in volume and the change in pressure during systole when it's totally contracted, and that affects contractility. This is the change in pressure over the change in volume of the arteries, the arterial system. This is referred to arterial elastance, and that is truly what systemic vascular resistance is. It's the change in pressure of the end systolic pressure over the stroke volume. Kind of cool. What's most important is that this line can change. You can have increased systemic vascular resistance and it will make the curve look like this, or you can have decreased systemic vascular resistance and it can look like this. Again, the most important thing is that afterload is proportional to diastolic blood pressure, and 95% of the time, an increase in diastolic blood pressure signifies an increase in afterload. But if you really want to get into pressure volume loops, you need to know this curve as well. Okay, changes in systemic afterload. You can see that this patient has a very low systemic afterload. This patient has a moderate systemic afterload, and this patient has the most extreme systemic afterload. You can also see that the diastolic blood pressure goes up here, here, and here. Okay, I swear we are almost done. We're going to finish by talking about changes in left ventricular compliance. Nice pressure volume graph. And remember the first curve I showed you when we were talking about this? This is the curve that helps signify preload, and it is the change in pressure over the change in volume, and it's the elastance of the left ventricle during diastole. Well, guess what the inverse of elastance of the left ventricle during diastole is? It's the compliance of the left ventricle during diastole, and it tells you how much pressure changes for how much volume changes as you fill the left ventricle. So this curve is compliance. When I first showed it to you, we were just talking about changes of a curve that is stationary. Maybe you have preload here, and you have preload here, and preload here, but the compliance doesn't change at all. But if the compliance change, the actual slope of the curve will change, and it'll look like this if you have decreased compliance, which is actually really important when you have diastolic heart failure. Okay, one last example. Here's a control loop, and you can see that this is the compliance curve right here, and then all of a sudden, the compliance curve gets stiffer, and you have a patient with decreased compliance, and for every change in volume, the pressure goes up greater. So, that's it for this video. In class, we're going to work through some problems. We're going to try to solidify the key points using problems. This is incredibly difficult. There's no one who gets it on the first time. And in the end, we want you to do the following, which I think you can do the first one, which is draw a pressure volume curve and label the axes and label the significant events. I also think you can already identify stroke volume and stroke work. I also think you can define ejection fraction and be able to calculate it from end diastolic volume, end systolic volume, and stroke volume. Finally, what I think is probably the most hard and will take some more time is how does the pressure volume loop change when it's affected by preload, afterload, contractility, or compliance and isolation? We are not going to do this grand exercise of a pressure volume loop and exercise right now. That we'll do in class. And with that, I bid adieu and thank you.